Hello everyone, my name is Ankit Agrawal. I'm a research associate professor in the Department of Electrical Engineering and Computer Science at Northwestern University. I'll be speaking today on Materials Informatics and Big Data, realization of fourth paradigm of science in material science. I'd like to begin by thanking the organizers for inviting me to give this talk, and also the numerous collaborations that I have in this space. Being a computer scientist, I actively collaborate with a lot of materials researchers and experts all over the world for most of my materials informatics works. In particular, I would like to acknowledge Professor Alok Chaudhary, who has been more than a mentor for me. I have learned a lot from him, and I'm still learning. And also, I'd like to thank the funding agencies, NIST, NSF, DARPA, and Air Force Office of Sponsored Research for supporting the works that I'll be presenting today. So, I'd like to start with a bit of background about what kind of works I do in general and our group as a whole. So, I strongly believe that in this era of big data, there are these two subfields of computer science, data mining and high performance computing, that need to be integrated more than ever before. So we call it high performance data mining, where we take these data mining algorithms like clustering and so on and scale them up to tens of thousands or even hundreds of thousands of processors to make them amenable for big data analytics. And then I'm personally very interested in also applying these high performance data mining algorithms in different domains like materials, healthcare, social media, bioinformatics, and so on. So, of course, in this talk, I'll be speaking mostly about our materials informatics works. Why I became interested in this? It happened back in 2011 when this Materials Genome Initiative, that I'm sure most of you are aware of, this federal initiative was announced, which aims at accelerating the deployment of advanced materials 2x faster and 2x cheaper. And data-driven analytics was specifically identified to play a major role in realizing the goal of this initiative. So that's when we got into this whole area. And as part of our efforts over the last 6-7 years now, I have these funded projects, part of the NIST Center of Excellence, CHIMAT, Center of Hierarchical Materials Design, which is a $30 million center, NIST-sponsored center, and I am privileged to co-lead the data mining efforts across the center. There's also an Air Force project on microstructure aspects of materials, a DARPA project on thermoelectric materials. I'm part of the NSF Big Data Spoke, the Midwest Spoke. There is a Northwestern Data Science Initiative, which is an internal funding mechanism where we're collaborating with Greg Olson on steel-specific data mining. And then lately, there has been a lot of interest from industry. A lot of companies have approached us over the past few months and expressed interest in learning and applying these data-driven techniques in their industrial workflows. So here is one such relationship with Toyota that has been formalized recently. So this is going to be the overview of my talk. I'll present some basic background about materials informatics and big data. And then most of the time I expect to spend on depicting illustrative materials informatics works from our group. And then in the end, I'll try to give a demo of some of the tools that we have. So let's begin. So this is one of my pet slides, paradigms of science. So if we look at how science and technology has evolved over the centuries, not just years or decades, we can very clearly identify these four paradigms of science. So till about 17th century, all science was purely empirical. Everything was based on observations. Today it is famous as the experimental branch of science. Then in 17th century, when calculus was invented, we could take real-world phenomena and express them as mathematical equations. So things like Newton's laws of motion or laws of thermodynamics in the material space, they are very good examples of the second paradigm of model-based theoretical science. Then when computers were invented in 1950s, we could take these equations and solve them now on computers and later on supercomputers. So this led to the third paradigm of simulations, computational science. And good examples of third paradigm in material space is things like density functional theory, molecular dynamics, or finite element modeling, and so on. Over the last 10-20 years, the sheer amount of data that has been produced from these first three paradigms that has far outstripped our capacity to make sense of it. So we have become very good at collecting more data, generating more data, storing bigger and bigger amounts of data, retrieving it reliably, and so on. But when it comes to analyzing and extracting actionable insights out of it, our ability has been rather limited. So that's why this fourth paradigm of science, that there's a big push of that for this fourth paradigm, which is big data driven science, where data itself becomes a resource. So in addition to all the physics that we know, all the domain knowledge, all the computational power that we have for doing simulations and so on, just the data, sheer amount and volume velocity of data itself, that is a resource in driving discoveries. So things like predictive analytics, clustering, relationship mining, anomaly detection, these are key techniques in this paradigm. So I have this invited article from a couple of years ago where I describe this in the context of materials. If you're interested, you can take a look. So talking about big data, there are different features of big data. You may have heard of different V's, and these three central V's, volume, velocity, and variety, these are the essential V's which differentiate big data from other kinds of data. And then there are other things like variability, veracity, which are features of any kind of data, including big data. The goal is to analyze in a way that we can extract value out of it and visualize it in ways for actionable insights. So needless to say, this whole process of big data analytics is nothing short of finding needle in a haystack. And I particularly like this example a lot because it not only signifies the difficulty in finding the right needle, but also it demonstrates the ease of finding the wrong needle. So in other words, if you're not sure exactly what you're doing, if you're not aware of the strengths and limitations of the data, if you don't have sufficient domain knowledge, or if you don't know the strengths and limitations of the algorithms or the techniques that you are applying on the data, then you can very easily fall into the trap of these wrong needles. And it is much more costly in engineering applications than any marketing kind of application. So for example, if I get an email from Amazon that based on your search history you may be interested in this, if I am, then great. But if I'm not, I can just delete that email. But if I make a mistake in engineering application, let's say I discover a new material which I claim to be very much optimal in, it has all magic properties, and I start making airplanes out of it or bridges out of it without proper validation, then that can be the cost of that is prohibitively large. So it's very important to have the right set of expertise in any materials informatics project in order to get reliable and trustworthy results. So if there's one thing, coming from a computer science background, if there's one thing I've learned from our collaborators in material science, then that is that everything in material science depends on these so-called PSP relationships. So this is very fascinating to me because I have worked a lot in other domains like bioinformatics, where everything depends on sequence, structure, function relationships. So there's a DNA sequence that gives rise to protein sequence that gives rise to protein structure and then function. And pretty much everything bioinformatics depends on that. So here, everything depends on these processing structure, property, performance relationships where science relationships of cause and effect go from left to right, and engineering relationships of goals and means go from right to left. And these are many to one. So in the processing space, there can be many different processing routes that give the same structure, that give rise to the same structure. And the same property can be achieved by multiple structures. So the forward problem of given a material, what's the property? It's easier, not easy, but it's easier. The inverse problem of given a property, what is the material? That's much harder and much more important for materials design. So what can data mining do? Materials informatics, which is essentially the application of data mining in materials, it can generate forward models for predictive analytics, where we can express property as a function of some representation, processing, composition, structure. And then if they are accurate, so they are almost always very fast because they are just data models. They don't depend on any differential equations or anything like that. So they're always fast, but if they're also accurate, and that depends on how you make the model, then they can also help in the inverse models, because inverse models are nothing but optimization problems, and it typically involves multiple invocation of the forward model. So if you have a fast and accurate forward model, it can help in the inverse models. And again, this is part of that invited article. So based on that, we have come up with this Materials Informatics knowledge discovery workflow, where the vision is to combine information from heterogeneous materials databases, and using a series of unsupervised and supervised learning steps, we can arrive at knowledge, which in this case is invertible PSPP relationships. So with that background, let's dive a little bit into the examples of the works that we have been doing over the last few years. So a lot of work in terms of forward models, which is a property prediction problem. So we have predictive models for properties such as steel fatigue strength, formation energy, band gaps, glass forming ability, bulk modulus, Seebeck coefficient, and so on. And then we have taken some of these models and solved the inverse problem of optimization or discovery, and we have been able to discover thousands of stable compounds, magneto-restrictive materials, semiconductors, metallic glasses, and recently we have also used it for inverse microstructure design. There is also some work on structure characterization, which is technically it's an inverse problem, but I list it separately because it has some unique features of image-based characterization tasks. So we'll discuss that separately. So each of these bullet actually is an hour-long talk in itself. So I'll not go into detail of any of these, but I'll try to give some highlights of some of these works. And then if there are questions, you are welcome to reach out to me over email. First example I want to show is steel data mining. Here we're using data from NIMS Japan, National Institute of Material Science. It has about 400 observations, experimental observations of steel with all the composition and processing information and the property of interest, which is rotating bending fatigue strength at 10 to the power 7 cycles. Using a supervised learning framework of pre-processing, feature selection, predictive modeling, and evaluation, back in 2014, we showed that we can generate highly accurate forward models, predictive models for fatigue strength. It was published in IMMI, and just in a few months, we got an email from the editor that our article has become highly accessed, because at that time these techniques were very new. Data-driven techniques were pretty new in material science, and there was a lot of interest around these. So over the years, from that point, we have actually improved upon these models by using advanced data-driven methods, ensemble modeling, and so on, and also developed an online calculator, which is available on this link, and I'll try to give a demo in the end, which is better than the previous models. For details, you can also look at the latest paper that we published in International Journal of Fatigue a few months ago. So this is one example of data mining on experimental materials data, which is small data from computer science standards, just 400 observations, but it is actually very big data from material science standards, because it took NIMS almost 50 years to collect this data, to generate this data. So this is an example of a experimental data mining. The next example I want to show is of DFT data mining. It's a collaboration between our group and group of Chris Wolverton here at Northwestern, who hosts the OQMD, Open Quantum Mechanical Database, and also researchers from University of Chicago and NIST. So this database, Jarvis DFT, that is hosted at NIST. As most of you may know, density functional theory, it's a simulation technique which takes crystal structure and composition as input, and then it can calculate many useful properties. So we wanted to make forward models, data-driven models based on this data. And the underlying problem here is data representation. So how to represent the material for the machine learning algorithm. So there are composition-based models where just based on the knowledge that, for example, ferric oxide has 2 atoms of iron and 3 atoms of oxygen, we can calculate a library of attributes like average atomic mass, average atomic number, electronegativity, SPDF electrons, and so on. And then this vector can be used as a representation for the material for building models on top of it. Similarly, we can use structure-aware models where we are using something known as Voronoi tessellations, where we can capture the local environment around the atom using this Voronoi cell and come up with attributes like average bond lengths and coordination numbers and so on. And then again, that vector can be used as a representation for data mining. And of course, structure-based models are more accurate because it has more domain knowledge. So there is this one direction of work where we are trying to collaborate with domain experts and see how much domain knowledge can we add into the model. But as computer scientists, we were also interested in something diametrically opposite. That let's say if we don't give any domain knowledge to the model, or for any reason, maybe it's not available or it's difficult to put, it's difficult to identify, or whatever it may be, then what is the best we can do? So we are using these deep learning models that many of you may be aware of. They have created practically an earthquake in many computer vision tasks and image processing tasks and natural language processing tasks over the last few years. Uh, and they are being used successfully in many applications like self-driving cars and speech recognition and image processing and so on. So, and the key advantage of these deep learning techniques is that it eliminates or at least significantly reduces the need for hand engineering attributes. So it can work with raw data, like raw pixels, raw speech signals, and so on. So here also we are doing a lot of hand engineering, right? When we are putting domain knowledge into the model. So we said, okay, let us not put any domain knowledge. Let's give it raw data. So raw data here is just elemental fractions. So for ferric oxide, we only want to give the model the fact that it has 40% iron and 60% oxygen. And it's iron oxygen, they are just IDs. There is no periodic table information that what is a group number, what is this, that, nothing. Just a vector of 100 or so elements and the fractions. And then we saw that as we give more and more training data to this model, here is the neural network architecture, then at some point it surpasses the earlier models. It surpasses the models that are encoding even domain knowledge. So first time when a student shows this result to me, actually I didn't believe. So people always tell me that they're skeptical of data mining, and I tell them that I am the biggest skeptic. So when something like this happens, I don't trust it immediately. So I sat with the student and we figured out what why it is working and whether it's working correctly or not. And we looked at some of the features of the network, like activations, that what exactly is happening inside the network in trying to interpret the neural network. And then we found surely that this model is learning the chemistry of materials at some level. So for example, it was able to know that lithium, sodium, potassium, cesium, these all are somehow more similar to each other than rest of the elements. Or for example, a group 1 element and a group 7 element when combined together tends to form a stable compound. We did not give any such information to the model a priori, but because it has had big data available thanks to OQMD and this availability of big data, it was able to learn this automatically, and that's why it is working better. So we're able to get up to 20% more accurate and 2 orders of magnitude faster models. And based on these, we also have a lot of inverse models, which essentially is a trivial idea. You just you make a forward model using a technique, and then you can use that to just scan everything. So let's say you want to scan all ternaries, so all the compounds of the formula AX, BY, CZ. So there are about 1 million combinations, assuming there are 100 elements or so. And with all the stoichiometries, there may be around 1 billion combinations. You just scan everything and then convert this set to a ranked list, which can be used to guide experiments and simulations, and then add it to the database. And then this iterative cycle has been shown to have a lot of promise to accelerate material discovery. Again, a lot of software available if you're interested to use it or in any way. And of course, papers. The third example I want to give is of thermoelectrics data mining. Again, similar workflow, just the property of interest is thermoelectric properties like Seebeck coefficient. The thing I want to highlight here is outlier analysis. So the way this data was collected was, it was extracted from literature. And a group of undergrads were fed some pizza and asked to read some papers and make an Excel file out of it. So when we used this data to build model, we found that the model is doing pretty good at, for the most part, but there are some outliers, as you may see here, which are very much off the diagonal. So the postdoc who was working on it couldn't help herself but actually go back to the papers and see what went wrong. So surely she found that there were systematic errors in the data collection. In some cases, the sign was missing. So the Seebeck coefficient is a bipolar quantity. It can be positive or negative. So some cases the sign was missing. So obviously that will have a big impact on the error. In some cases the magnitude was wrong because the student just collected the wrong number, because they are not experts in material science. They are just undergrad students. So they did whatever best they could do. But this study, to our surprise, we didn't start off with that, but it kind of showed that data mining can help in at least like automatic or at least semi-automatic data curation, which is very important issue right now for many materials databases in general, but specifically for materials because their data is small in general. Moving on to microstructure space, this is a collaboration with Surya Kalizindi from Georgia Tech, and here we're looking at the homogenization and localization problem. So given a two-phase composite, when we apply a loading condition at the macro scale, how does the strain gets distributed at the micro scale? That is what the localization problem is. Typically, it is done using finite element modeling that you see here. So there are these hotspots, that the red spots where the strain is maximum, and that's where the crack is expected to initiate. And it takes around 45 minutes to do a finite element simulation. And we are trying to see whether we can do the same using data models. So here you see there are four different scenarios. As you add more and more domain knowledge into the model, like the far right, you see 2-point statistics based data mining models. So there we can very accurately reproduce these hotspots and in a fraction of a time. So down from 45 minutes to less than a second, plus a one-time training cost, which is a few minutes. So this can be very useful for this this workflow of FEM-based calculations. And recently we also tried deep learning on this, and I'm not showing the results here because they are currently under review, but they have been significantly more accurate than the current models, up to 50% reduction in error compared to what I'm showing right now. This is another example of a microstructure optimization, so inverse problem, a collaboration with Veera Sundar Raghavan from University of Michigan Aerospace Department. The material of interest here is magnetoelastic iron gallium alloy called galphenol. Just like thermoelectric materials convert heat and electricity, magnetoelastic material can convert elastic force to magnetic field. So they have applications in actuators, sensors, aerospace industry. Forward models are well known, that's not a problem, but the inverse models are a challenge because of high dimensionality. So back to the DFT example, we had 3 dimensions there, right? If you're looking at ternaries, there are 3 dimensions, and we can just scan everything. It's just a billion or so combination. But here, because microstructure is a continuous thing, and we here used orientation distribution function, a 76-dimensional orientation distribution function, ODF, for representing the microstructure. So even if you assume there are just 2 possible values for each dimension, 2 to power 76 combinations are enormously large to be able to scan everything. So in fact, we did some calculations that even if you have a very fast forward model of just 1 microsecond, then even then it will take more than 10 billion years to calculate or to scan everything, to scan the entire space. So that's prohibitively expensive. So we came up with this data-driven approach of random data construction, search path refinement, and search region reduction, which are based on feature selection and decision tree-based methods. And that helped us, achieving up to 80% faster and 20% better solutions than traditional methods. And more importantly, for the first time, multiple solutions were discovered. So if you remember the PSPP figure, the inverse models are one to many. So we want to be able to identify as many materials as possible which optimize a property. So here you see 26 structures, microstructures that optimize the magnostrictive property. And this was back in 2015, Scientific Reports is where it was published. And then recently, one of our students added a tolerance parameter to it, by which he has increased this from 26 to thousands or tens of thousands microstructures which produce a property within 0.0001% of the optimal, something like that. This is a structure characterization work, so image mining now, in collaboration with Mark de Graaf from Carnegie Mellon. And here the problem is, given EBSD, electron backscatter diffraction image, can we infer that which orientation it came from? What are the 3 Euler angles, or the angle triplet we want to infer? So we developed a deep convolution neural network based model for this with a customized loss function, because these numbers, these angles that we want to predict, they are numbers, but they are special numbers. They are periodic. So like 1 degree and 359 degree is very close to each other. So we came up with this customized loss function, cos inverse of cos of the difference of angles, so that everything is mapped to 0 to pi, and it increased the training cost a lot. So you can see it almost takes a week to train these models, but it's very fast, order of magnitude faster, and about half the error compared to the nearest neighbor with cosine similarity, the state-of-the-art method that they're using. So this was published in Big Data, which is a top computer science conference a couple of years ago, and material science journal paper is currently under review. This is a recent work in collaboration with Wei Chen from Northwestern, where we are using something called generative adversarial networks. So here we have not one but two neural networks. One of them is called generator, and another is called discriminator. So a simple, commonly used analogy to explain this is given normally, that you can think of generator as a group of criminals who are trying to produce fake currency, and discriminator as the police who's trying to catch them. So as you train both these networks simultaneously with more and more data, they kind of make each other stronger and stronger till they achieve the Nash equilibrium, the theoretical Nash equilibrium, and at that point the generator can be used for some useful work. So here you see the original microstructure, the real microstructure, and these are the generated ones from the generator that not only visually look similar but also are confirmed to be similar by statistical analysis, two-point statistics, and so on. And they can also be used in conjunction with an optimization method like Bayesian optimization. And with just about 100 iteration, we can get to the optimal microstructure. In this case, it's an optical property of the microstructure. Which is so this optimal microstructure was found to have 142% better property than the traditional microstructure, than the traditional techniques what they can give. And then there are some other advantages which I don't have time to go into, but it is all documented in this paper, which just got accepted. It should appear soon in Journal of Mechanical Design special issue. I think this is my last example. So till now we looked at micro scale images, data mining on micro scale. We have also shown that we can do the same thing on macro scale images. So we were looking at pavement images from Federal Highway Administration LTP program, and the goal here is to distinguish between crack and non-crack images. And look at the data size; it's just 1,000 images. People typically believe that for deep learning we need big data, huge amounts of data, which is true. But when we don't have that, there are other ways you can get around it. So there is something called transfer learning. So here we are using a pre-trained model called VGG16, which is pre-trained on ImageNet, which is a very big data set of images, 15 million plus images, and use that network to get features on these images and then use it for data mining. So with that, we were able to get up to 90% accuracy of classification, and this was published in Construction Building Materials recently. And then very recently, we have taken it to the next level. We have collaborated with a drone company, which is taking images of these infrastructure, buildings and so on, where it is difficult to manually go and take pictures. And again, the problem is same, crack detection. But look at the image dataset size, an order of magnitude smaller, just about 100 images. But again, because of this transfer learning approach, we are able to get up to 90% accuracy. So this again just a proof of concept for now. But we can apply these techniques in all kinds of problems if there is proper expertise on the table. So these are some of the works that I described, some of them. And if there is a couple of minutes, I would like to give a quick demo of some of the tools that we have developed. So it's all available on this link, info.ecs Northwestern EDU. So in material science, we have, for example, the steel fatigue strength predictor. You can put a steel of your choice, composition and processing, and it can give you prediction of the fatigue strength in real time with quantified uncertainties, which is very important for any prediction. And then the same thing you can do for there's a formation energy predictor. You can put the compositions of your choice, and it can give you predictions. So the deep learning model is the most accurate, but you can use other models also if you like. And then there's a thermoelectric toolkit where there are models for Seebeck coefficient and bulk modulus. So here again you can put a composition information, even a doped composition, as you see here. It's a doped composition, and it can give you the Seebeck coefficient predictions at different temperatures, because it's a temperature dependent quantity. So here you see it is all negative, and it is increasing with increasing temperature, which is expected. And negative means it's a N-type material. And similarly, for bulk modulus, you can put a CIF file. You can upload a CIF file, and it can give you predictions. So I'm not going to show that because of lack of time. And so these are some examples of the material science tools, and there are also similar tools in other domains like healthcare, and you're welcome to check them out as well. So I'd like to end with this take-home message that the key to success in this materials informatics is interdisciplinary collaborations, because for some strange reason the fields of material science and computer science, they haven't talked to each other as much as they should have. Biology and computer science, they started talking back in 80s 90s, so bioinformatics is a very mature field right now, but that cannot be said for materials informatics. So I think that is really the key, because there are so many techniques in computer science that are just waiting to be applied. It's just that we don't know the problems, the existing problems in material science, and hopefully you know all the problems and we can work together to solve them. So I think more computer science participation is very much required, and I'd very much like to see community as a whole going towards that in the future, coming years. Thank you so much for your attention. If there are any questions, please feel free to reach out to me on my email here, and I'll be happy to get back to you. So thank you so much for your attention. Thanks.